There's now 113 people in the class of 15 minutes ago or so, and none of the sections are full. None of the lab sections are full. So if you feel the need to change section, you can now. How many people tested boards, have running boards? So maybe a quarter of the class, maybe a third, maybe probably a quarter. I found 2 boards in the lab that had been started and abandoned because there was an error on them. That annoys me. You make an error, you fix it. I'll help you fix it, but you fix it. You don't leave it on the board because you don't leave it on in the trash because the first resistor, yeah, I dig through the trash. You don't leave it in the trash because the first resistor you put on was the wrong resistor. So, any questions about building boards? Monday morning, 8 a.m., be in there again. We have to be out of there by 1 p.m. on Monday. Well, we'll have to be out of there by noon so we can have lecture. Then on Tuesday, we can be in there in the lab from morning until 1 o'clock when 2300 starts, except I got to go to the doctor, so I won't be there at the crack of dawn. Nobody has so far requested Tuesday time to build stuff. You requested, I'll be there. Requested on Piazza. And I'll tell you, then I think I can be there by like 10, but I just don't know yet. My doctor's slow. Any questions about building boards? Any questions about the reading?
The software installation, the plib link is the same link as the compiler's link?
There are 3 different links. Go ahead.
You just Google the download archive. Stuff like that.
Google download archive at Microchip.
Yeah.
Or you could follow the suggested links that are on Lab 1. But there are 3 separate things you need to download. One is MPLABX, the second is the XC32 compiler version 1.4, and the third is plib. I believe that there is a problem installing that version of the compiler on the newest version of Apple operating system. So you may not be able to run the old version of the compiler that we have in the lab with the new version of whatever they call it, OS 10. You may have to go to a newer version of the compiler. Anybody have any experience with that? Go.
Yes, you need to turn off a security policy of the Mac, and you can install the compiler, and you can turn it later on.
So you have to turn off a security policy and then you can install it. Well, that's good to know. You want to put that on Piazza, please? That'd be great. Okay. Then we'll all know. What else? Any other questions about the reading? A lot of reading. If there's no questions, read some more. So let's talk a little bit more about introduction to the course, since I didn't quite finish that. Then I want to start talking about Lab 1 because it starts Tuesday evening, Tuesday 4:30. I will be at all of the labs for the first week. I want to make sure the TAs are tuned in. I want to make sure that all the hardware works. After that, I won't be in the evening, the 4:30 sections, but I will be in the afternoon sections, including Wednesday when there's no section if you want to come in and work. I like to go in there and sit around on Wednesday afternoon and see who shows up. So, any questions about the logistics of the course, how grading works or assignments, the staggered assignment schedule? Yes?
Are we going to need to download everything onto our laptops, or are there computers on the lab?
You don't have to download anything. You can use the machines in the lab have all the hardware already installed, software installed, and you don't have to download anything. People find that they want to be able to compile at home, but you don't have to do that. We're going to be open a lot. So, as I said last time, we're going to be talking about, primarily in lecture, about how to control the peripherals on this chip from C. I assume that you all know how to write a state machine in C, and we're going to talk about a threading package, which is extremely straightforward to use, and we'll use for organizing the C program flow. But most of the intellectual interest in this course is controlling real-time peripherals for good performance. So we're going to spend a lot of time talking about how to configure peripherals, how to have them talk through pins, how to have them interact with the real world, and how to get data back into the chip. Since you're going to be working with real wires connected to a real CPU, this isn't virtualized in any way. Code that you write can break the chip, can burn it up. If you hook two pins together, make one an input, one an output, that's fine. You make them both outputs, make one high, one low. You have two voltage sources hooked together. What happens? What's the Thevenin resistance? Oh, you need that for a homework 1. Haven't done that yet. Enough current flows to burn up one of the pins. Whichever one burns up is the one that has the smaller transistors. There'll be no symptom except now your code doesn't work. So there's a couple of corollaries of this. One is, since software is managing real hardware, you can't take any of my code and simply cut and paste it into your code without knowing what each line does. If I turn on a peripheral that you don't use, and you cut my code into your code, that peripheral is turned on and running a pin whether or not you use it. Therefore, if you cut and paste code, you must know what each line does. I shoot my own foot off this way. I cut and paste some of my old code. Where the hell is that? What's going on? And I've turned on a peripheral I forgot I turned on. And I go back and I plod through and I look at every line and turn it off. So think carefully. You're going to have to look at every line of code that you use in a program to figure out what it does. Secondly, since you're handling hardware, you're going to burn some stuff up. That's okay. We'd like you to learn from your mistake and not burn too much stuff up. And believe it or not, I have seen this happen. Student will build this circuit, VDD. Make sure I get this beautiful thing right. They actually use a single pole, single throw switch and hook the port pin to here. And they'll say, it's really weird. When I push the button, the system crashes. And in the old days, when we had fused power supplies, you push the button, it blows the fuse. I had one student who blew 500 fuses one semester. That's an example of kind of not learning what's going on. So, the obsessive programmer will protect the I/O pins with the following circuit. Every single port, so we should mark this, don't do that. What you are going to want to do is, whenever you hook a port pin to anything, that you don't know very well or where you might change the I/O direction, put a 300 ohm resistor to the port pin. That won't slow down the signal very much from RC loading, and it'll do an impedance protect on the port pin. That's why we go through 10,300 ohm resistors a year. That's okay. I would prefer to do that. Secondly, of course, for this particular circuit, you're going to put a pull-up. You're going to put a pull-up resistor here so that when you close the switch, a finite current flows. So always protect port pins unless you are absolutely sure you know the direction of the I/O direction. And oh, by the way, does anybody know the default direction, input or output, for the PIC32 at boot time? It's actually in the port pin description, and it's puzzling to me. The hardware designers at reset turn all of the port pins, port A and B pins, to output. That means none of them are impedance safe as soon as you turn them on, as soon as you boot the system. Use protection resistors. And since we're going to be hooking up wires, you are going to have to worry about Thevenin equivalent impedances, and that's why that's a homework problem for lab 1. You're going to have to worry about filtering. You're going to find that serial peripheral interfaced clock lines produce giant spike trains when they're near the analog to digital converter input wires, because even though you don't build the capacitance between the wires, it's there. So you're going to have to worry a lot about secondary effects. The MP Lab GCC environment includes a bunch of libraries. There are the usual C libraries, stdio.h, which is standard I/O. That gives you printf, fprintf, sprintf, all of those, the usual C stuff. There's standard lib, which gives you rand, A to I, and a few other standard functions. But there are also going to be several libraries that either I or Tahmid wrote that you're going to want to link up with most programs, and we'll go through those. And then there's going to be plib, which has all of the I/O descriptions for every register in the machine. There's something like 1,000 I/O registers that are named. So there's going to be a bunch of library work we need to do to go through to get things set up, but we won't be doing it all at once, so it's handleable. This CPU has a huge 32K of RAM. All right, so every variable you define has to fit into 32 kilobytes. So you define all floats. On this particular architecture, a float and a double are both 4 bytes. To get what would normally be called a double in, say, MATLAB, you have to say double double. So a float and a double are 4 bytes. An int is 4 bytes. A short is 2 bytes, 16 bits. And a char is 8 bits. And you may want to choose the data length correctly to optimize memory use, because you're going to run out of memory. To make things more interesting, there's 128K of flash, which was where you'd normally put program code. However, if you have a large static array that never changes, let's say it's a lookup table of exponentials or sines and cosines, you could put those tables that you never write into flash and save RAM. I'll show you how to do that. There's an internal oscillator on this chip so that you do not have to have an external crystal. If you want high timing accuracy, you do need the external crystal, because the internal RC oscillator is only guaranteed to 0.9%. It's good enough for most stuff. In addition to the internal oscillator, if you read the oscillator section of the hardware reference manual, which, oh my goodness, that's a piece of work, there's a phase lock loop built into the, you know what a phase lock loop is? Everybody know what a frequency multiplier? So you can take the base frequency of the internal oscillator, which is 8 megahertz, and you can set it to any rational fraction up to about 80 megahertz in steps of 4 megahertz or so. You can set it to any frequency you want. The output of the phase lock loop can be higher than the input frequency. And in fact, you can set it so high, the CPU won't run. Because some variants will run up to 80 megahertz, ours won't. Ours is guaranteed to 50, but it runs at 60 often. Now, if you drop it in ice water, it'll almost always run at 60. But on the tabletop, you're guaranteed to have 50 megahertz. So we have to talk about how you configure the phase lock loops to give you the frequency you want, which is usually the highest possible because you want performance. But occasionally, you might want to save power. And then you could drop to a lower frequency if most of your application depends upon the oh-so-slow human. There's no reason to run the clock at 50 megahertz. You might as well run it at 2 kilohertz. So there are ways of slowing the clock way down, and we need to talk about that. There's at least 3 different serializer, deserializers on this chip. There's serial peripheral interface, there's I2C, and there's UART, all of which have different characteristics with different uses, speeds, and so on. We're going to mostly use SPI for the first part of the course. It's a simple protocol and it's fast. And there's some other things that are available on the chip. One is, which you're going to use in Lab 1, is a analog comparator. Inside the CPU is an op amp with 2 inputs and no feedback. It is a very fast comparator. It's fast. It'll switch from on to off output, off to on and on to off in less than a machine cycle. And this output, these 2 can be configured as inputs from the outside world. This can be configured as an internal signal, or it can be routed back to the outside world. So now you have a small analog thing inside the chip, and we're going to be using that in Lab 1. And in fact, we're going to be using it we're going to be using this signal as a trigger to capture the value of a timer. There's 5 timers on this chip. There's 5 timers, 5 16-bit timers. One is being used by the threader. There's 5 output compare modules. What does that do? You route a timer through an output compare module, and you can get a PWM, or a square wave, produced in hardware with no software cycles necessary. So the CPU doesn't have to switch the waveform. The timer talks to the output compare, which talks to an I/O pin in hardware. So that's one example of a peripheral chain that will save your CPU a ton of time if you're synthesizing PWMs. Let's say 5 PWMs for 5 servo motors. You can do that with 0 CPU cycles. There are also 5 input capture modules. Input capture, which will you can think of them as a register whose input is a timer and whose load clock is an event. An event from the outside world could be an edge. It could be an event from inside the CPU also, say an interrupt. But the edge we're going to use in Lab 1 is the edge which comes from the comparator. So we're going to route the comparator to the event capture so we can detect, as we start to charge a capacitor, I'm going to go into more detail, as we start to charge a capacitor, we can find out within a machine cycle when it passes a threshold. Because the comparator will switch from high to low or low to high. We'll take that edge, we'll capture a timer, and we know precisely when that edge occurred. And if you know the time it takes to charge a capacitor and you know the resistance, you can get the capacitance, which is what you're going to do. So you've got this gigantic toolkit of stuff in the CPU. You've got all these output compare channels. You've got these input captures. You've got these timers. Certain timers, they're not orthogonal. Some timers have special functions. Timer 3 can trigger the A to D converter automatically. So timer 3 can talk directly to the analog to digital channel, to the A to C converter, which can talk to the DMA controller, which can grab the ADC data and put it in memory. So you can have a timer ticking away, grabbing data from the analog converter and putting it in memory with no code executing. No interrupt service routines, no code. That's cool. It's also confusing. That's why we need to talk about it. There's also some higher level stuff, a USB on-the-go controller, DMA, which I mentioned, and peripheral pin select, which we're going to talk much more about. Any questions about the CPU? It's an interesting CPU. It's not a monster like an ARM, but it's got a lot of stuff on it. For Lab 1, we're going to use I/O functions because we're going to be switching a pin back and forth from input to output and output to input to charge and discharge a capacitor. And we're going to be using the PPS, the peripheral pin select system, to map signals to the outside world. And we're going to be using the comparator and an input capture channel to measure the time necessary to charge the capacitance. So if there's no questions, if there's questions, I'll take questions. Otherwise, I'll go ahead and start talking about the horrible details of Lab 1. Questions? The goal of this course is to figure out how to use all of this hardware at the same time to do some function. Right. Now, clearly, you're not going to use every single unit in every single application. Motor control might use more PWMs. instrumentation might use more input captures. Let's say you're measuring sonar channels. Let's say you have an array of microphones and you're trying to get the direction of the gunshot. Well, let's settle for a clap. You're trying to get the direction of somebody clapping. So you need to measure the arrival times from different microphones. That would be a clear way of using input capture to get times, right? So depending on what you build for a final project, what we make you build earlier in the semester, you'll use some subset of these components, and we're going to make you try and we're going to set it up so you use most of them. So again, any questions? So what we're going to do is we're going to write a program that uses this circuit to measure a capacitance. You're going to know this resistance, but you're going to calculate that. You're going to know the resistance. You're going to put this through a 100 ohm or 300 ohm resistor or so. You're going to run this into the CPU. Now, this is outside the CPU. This is inside, where there is the comparator. This is the positive input. The negative input of the comparator is going to go to yet another peripheral I haven't mentioned, which is a internal precision voltage source that produces 1.2 volt plus or minus 0.06 volt. So, then the output of this, the signal name here, by the way, of this, the internal signal name is C1 out. The signal input name is P1 in. Because of the internal architecture of this particular CPU, we have to route this back out of the chip and back in through another pin to the input capture. So this will be IC1, input capture 1 signal. And we're going to route C out, C1 out into input capture in by wiring 2 pins together. Oh, resistor. Okay, 300 ohm resistor, because you never know. You set both of those to outputs, fire one high, one low, one's dead. Then you'll bring me the chip and I'll say, use channel 2. So what we're going to do, though, this, by the way, on the package is pin 7. This is, we're going to map this to pin 18. There's a step using the peripheral pin select I haven't talked about yet. And we're going to map this to pin 2. So pin, oh, that's horrible. Pin 7, pin 18, pin 2. Pin 7 also happens to be known, oh, this gets so messy. So the internal signal is called P1 in, and that is mapped to pin RB3, which is also bit 3 of the B IO port, of IO port B. So what we're going to do then if this is VDD, and this is 0, and this is about 1.2 volt here, then we are going to switch RB3 to an output and set its value to 0. Output a logical 0, 0 volts. When we do that, we will discharge RB3, pin 7, towards 0. Because now this pin will be held at 0 through 100 ohms. If I want to get this near 0, though, R has to be much, much larger than 100 ohms, because this is a voltage divider. What I care about is the voltage on the capacitance, right? So we want at least 100 to 1 voltage divider here. So this has got to be greater than what? If we want 1%, if we want to get to 0 within 1%, how big does R have to be? 100 times bigger, which is 10 to the 4th. So, bigger than 10 to the 4th ohms. After we wait long enough, compared to what? Well, long enough, 5 time constants. 5 time constants of what? 5 time constants of C times 100 ohms plus the Thevenin impedance of the port pin.
I thought we didn't know C in this out of this one.
You don't, but you know a range. I specified in the lab that it's going to be between 1 nanofarad, I haven't gotten there yet, between 1 nanofarad and 100 nanofarads. So you can upper bound it. So it has to be able to discharge 5 time constants at the upper bound. After you do that, then we're going to switch RB3 to an input. RB3, what's the input impedance of a CMOS input under sort of standard conditions? If you have a CMOS gate that's not connected, that's free floating, what is its Thevenin input impedance? Does anybody have a feel for that? From some analog class or some circuit class or something? Did you say something or no? Damn near infinite. Whatever that means exactly. Nearly infinite. On a log scale? So, the only thing I know of that makes any sense to say that way is 1 job offer is infinitely better than 0 job offers on a log scale. So this input is really high impedance. That means no current flows through here when you change it to an input. So the capacitor starts to charge according to the RC time constant of R and C. So this charges up towards VDD. If we measure the time at which we switch if we measure this time and we measure the time, turn off your damn cell phones, will you? My doctor reminded me I have an appointment. So, if we measure this time, then we have all of the information we need to measure the capacitance. This question?
I was slightly confused. What was on the y-axis?
Voltage, VC. Thank you. So in fact, VC Vc of t, of course, is given as VDD times 1 minus e to the minus t over tau, where tau is equal to RC. And if we know that the voltage at some time, some delta t here, is 1.2 volts, we know everything we need to solve for C. You're going to need, however, to calibrate this 1.2 volts because plus or minus 0.06 is not quite accurate enough. So you're going to have to figure out a way, there's at least 3 or 4 ways of calibrating that voltage, of knowing what the exact value of the threshold voltage is. It might be 1.23 or 1.19. But that's a homework question also. Figure out how to get that voltage. Any questions on this? So, now we need to look at the peripheral pin select, because while this pin is fixed, RB3 is always P1 in. Where does it say that? Oh dear, let's see, where does it say that? It says that right here. I hope. RB3 is pin 7, which is C1 in A. So that's the positive input. It's also connected to analog 5, the I2C clock, the real-time clock control, and something called RPB3, which is the output of a multiplexer on peripheral pin select. You can only choose one of those that's connected to the port. By default, nothing else is going to be turned on. RB3 is connected to C1 in A. We do not have to choose that through peripheral pin select. We do have to choose which pins are going to be mapped to C1 out and in IC1. If you scan through all of everything on this you can't see what I'm gesturing at there. If you scan through everything on here, you won't find IC1 because it's in peripheral pin select. So let's go down to the peripheral pin select input table. Yikes. And we look for C1 out. No, let's look for IC1 because that's an input. Oh, I see IC4 there. Nope, that's not right. IC3. No. IC1. So IC1 is a signal in group 3. Group 3, I added the group 3 on there because the original documentation doesn't tell you the group numbers. You just had to guess what that meant. So IC1 is a signal in group 3, and it can be on any of these pins. A2, RPB6, RPA4, RPB13, and so on. I'm going to choose to put it on RPB13, and if we go back, this is why you need more than one window open here. If we go back, RPB13 maps to pin 24. Uh-oh, That's not what I put down here. I said pin 2. Why is that? It's because I didn't see the 4 on my diagram. Pin 24. That's not even a typo, it's a braino. So, pin 24. So you have to go through these 2 steps of identifying the name of the signal on the peripheral pin select, get the group number, map it to an I/O pin, and then that's mapped to a physical pin, which in this case is pin 24. So RPB 13 maps to pin 24. Now we do the same thing for the C1 output. So now we go to the peripheral pin select output table. And we scroll down looking for C1 out, which is, I'll save you the pain, it's in group 4. C1 out is right there in group 4. And so we can map that to A3, 14, B14, B0, B10. And I chose to map it to B9, RPB9, right here. No reason. This is one of the first things I did, so I just plucked it out of the air. RPB9, then we go back to the data sheet, the pin out. B9, RPB9 is pin 18, which is what I correctly wrote here. So you can think of the peripheral pin select as an 8-way multiplexer that allows you to choose one of 8 pins that is attached to any I/O, almost any I/O signal. The SPI clocks have a fixed I/O pin. I wish they didn't, but they do. A few some of the comparator inputs have fixed I/O pins. Most of the signals are on peripheral pin select, and so you have to go through this 2 or 3 stage process of mapping a signal name to a pin select to a port pin number. Now, mercifully, we've done that to some extent for you, at least at the beginning. So,
Question?
yeah.
So, all right, so you told us that the signal name was IC1, for example, but in the real world, how would we know that?
You would look at the hardware reference manual. So let's go look at the hardware reference manual for the comparator. Okay, hardware manual sections. Comparator. Introduction, probably. So we have the diagram which says that the signal name is C1 out, and here the specification is C1 in positive and C1 in negative. However, in PLIB they made it C1 in A and C1 in B. How did I figure that out? Looking at the source code. Now we go look at the, what do we need? We needed the input compare. So now we go down and look at the input compare, input capture, introduction. Yikes. So we've got inputs from either timer 1 or timer 2. We've got interrupt generation. Where's the input? ICX input, where X has a value from 1 to 5. So that's the signal name at the input. We're going to give you lots of examples that instantiate these peripherals without you having to decode all of these steps, at least for the first time. If you want to do multiples, you'll have to decode them, but we're going to give you templates for simple instantiations of these, at least for the first lab. So, maybe we ought to look at just a little bit of code now. No, we only got 5 minutes. 5 minutes. That's not enough to even take a deep breath and look at the header code. Any questions at this point? So, for all of these labs, what you're going to be doing is you're going to be looking at the peripheral hardware manual, you're going to be looking at PLIB, you're going to be looking at the peripheral pin select, and at the chip pinout. So mostly when I was developing this, I had 4 windows open, cycled between them until I memorized them. So, CMOS inputs have infinite input impedance. What happens if you leave a port pin as an input unconnected? What is its voltage value? Anyone? Yes?
Is it floating?
It is floating, which means you don't know. It can be any value. Now, could it be 1,000 volts? Mercifully not, because if you look at the input, the details of an input pin, it has a Schottky clamp diode up to VDD and another Schottky clamp diode down to ground, so that the voltage can't go much above VDD or much below ground. And then the input of this thing really is just a CMOS gate, right? That's horrible. And you can turn on an input, particularly one of the analog inputs where you can actually measure voltage. Turn on an analog input, don't connect it to anything, move your hand back and forth, and you can change the voltage on the pin. Oh, that sounds like a capacitance switch. And it is, in fact. These pins are extraordinarily ESD sensitive if they're not terminated. That means you will never set a pin to input and float it, because the logic value is random. Let's say that you happen to be right at the CMOS threshold, and somehow the voltage gets stuck at the CMOS threshold, so through no fault of your own because it's floating. The current that flows through the gate and through the inverter is now very large and can blow up the input pin. So, but wait, there's more. There is an optional internal pull-up resistor that goes to VDD through a switch, which is controlled by software. There is an optional internal pull-down resistor, which is connected to ground through software-controlled switch. So that you can force a pin, a disconnected pin, to always be weakly high or weakly low by turning on the appropriate by turning on the appropriate pull-up or pull-down resistor. And you will do that for Lab 2, where you have to hook a keyboard to it, you have to hook a keypad to an I/O port, and when the switch is open, when you press the button, it's grounded. When you let up on the switch, it's floating. So you turn on a pull-up resistor, and now it's not floating anymore. We got a minute or two. Time to talk about final projects. It's important. Half your grade. So, any ideas for final projects? Anything you've come in with? I mean, this is not necessarily from this course. Anything you've always wanted to build? Yes? You have a smile on your face like you have an idea.
Sure.
Sure. Well, yeah, okay. No?
Like a single ducted fan, like thrust vector controlled, like landing vehicle. like a small flying vehicle.
Okay. I want to know exactly how you're going to test this without tearing the lab apart.
It's all encapsulated.
I know, but yes, but I don't want this thing flying across the room and landing on somebody else's project, right? Tether. All right. I want to hear a lot more about it before that. It's a good idea, but I want to hear a lot more about testing. What else? Anything else? Start thinking, folks. It's only 5 weeks away when you have to write the proposal. Oh my God. Okay, I'll see you Monday. I'll see you Monday in lab at 0800.